you hear me? Excellent. Okay, I'm going to talk about splay faults. This presentation in parts is going to look very, very similar to the presentation Jennifer gave earlier today because I'm using many of the same methods to combine GMPEs. And then I'll show preliminary results then made from the broadband platform, combining the time series then to produce the response spectra for the splay fault simulations. Okay, so this is a map to show the simulations that were run. The black line is the Hosgri fault, the red line is the shoreline faults, the green is San Luis Bay, and the magenta is Los Osos. And so what I'll be showing then for the simulations is combining the Hosgri faults in the time domain with each one of the splay faults to produce the response spectra. And when we do this, we're using fixed hypocenter locations. So the hypocenter on the Hosgri is going to be up the northern end, and the hypocenter is located halfway down dip. So we have different scenarios that we ran. For the thin case, I'll be showing the results from the thin case. The crust is 15 kilometers thick, and the Hosgri fault's vertical. So then the hypocenter is at 7.5 kilometers then. And then what we do is we let the rupture propagate down the Hosgri, and we have another fixed hypocenter at each junction point. So the Los Osos hypocenter here, shoreline, and San Luis Bay. The blue dots represent the locations where we calculated simulations, and today I'll be showing simulations at Diablo Canyon, which is the red dot, right there. Okay, so all the results that I'll show are for this thin case. Towards the end, I'll show a comparison of the response spectra for all three of these different cases, but we'll come back to that at the end. Okay, these are example time series for the Hosgri fault in the black, the Los Osos fault in the red, and then the composite seismogram here in the blue. This is just east-west component. And why I'm showing this is we are approximating the time that the Los Osos initiates here by using this distance divided by 0.8 times an average shear wave velocity to get us in the ballpark. So that means there's a delay of about 5.5 seconds for this time series here. So we scoot this over 5.5 seconds, and we combine them. And what I really want you to pay attention here is when similar types of waves are arriving at about the same time to give you a composite. Thanks. Okay, yeah, when similar types of waves are arriving at about the same time to give you a composite, the response spectra, there's not much change. So what I'm showing here is the response spectra here computed with a time shift of 5.5 seconds. That's assuming a shear wave velocity of 3,000 meters a second. This is a time shift of 4 seconds, assuming a shear wave velocity of 4,000 meters a second, which is ridiculously fast, and a time shift of 8, assuming a shear wave velocity of 2,000 meters a second. And this is the difference it gives you in ground motion. Okay, the next example, we have a larger distance here between the hypocenter location and the initiation of the hypocenter for the shoreline fault. So we have larger time shifts. So now when you look at the time series, probably the next slide will show it a little bit better, we're starting to see that we have different types of waves arriving in time. So this looks quite different than these scenarios here. And we're starting to see that it's going to affect then the ground motions. So when Julian says that there could be time delays when a rupture initiates and then propagates onto the next fault, this might be something we want to start paying a little bit of attention to. Okay, so this should look familiar. Jennifer had 3 different methods of combining the GMPEs. I have 4 because it gets a little bit more complicated than with the display case, just a little bit more to keep track of. The first method is using, it's treating display like 2 separate earthquakes. So you're using the closest point to each segment, so the closest point to the Hosgri or the main is in the display, and then we're using an SRSS method to combine the GMPEs or combine the response spectra. Method 2 is using a weighted average, weighted by segment length. and then using the closest point to combine. Okay, so method 3 computes the magnitude based on the total, the main plus the display, the combined rupture. And then it's using a weighted average based on 1 over r squared for the dip and the rake to come up with the parameters to put into the GMPE. And then method 4, I think this is the one that's different between what Jennifer showed and what I'm showing. We're using the magnitude calculated from the total area and then the parameters for the closest point, whether it happens to be on the main fault or the splay. And then method 5, just the simulations. And I also want to mention that Jennifer produced all these GMP plots for me, so thank you. Okay, so this first figure then shows the closest point, the results for the closest point. So here, the Hosgri, we're using a magnitude of 7.2 in the GMPEs for a Hosgri. It's a vertical fault and a rake of 180 degrees. And the San Luis Bay, we used a magnitude of 6.4, a dip of 70 degrees, and a rake of 90, and then the SRSS was used to combine the response spectra. Method 2 uses a weighted average, so now we're using a magnitude of 7.4 in the GMPE. It's near vertical, 87 degrees dip, and then the rake of 167. So fairly similar. Okay, method 3 is the weighted average using the 1 over r squared technique to calculate then the dip and the rake for the GMPEs.
Katie, can you go back? Because
Sure.
you said the last one's fairly similar. There's some significant differences there, right? So if you look at Campbell and Besorgnia at 10 hertz.
Yeah, this one is different.
Right. So the SRSS scene is producing a much bigger value in this case than the other one.
That's true.
Right.
Okay. So then this is showing then the weighted average and the combined rupture. And so what I mean by combined is we are using the magnitude for the total system, so the total area of the magnitude plus the splay, and the dip and the rake of the closest point for those. And then this is the results of the response spectra that were computed from the combined time series for the Hosgri and the San Luis Bay. And then this just overlays the simulation results in color with the different methods. So then this is the closest point combined with the SRSS. This is the using the total area of the main fault plus the splay and the average properties along the fault weighted by length. This is using the average properties weighted by 1 over r squared. And then this is the total area using the geometry of the segment that is the closest. That's a lot to say. Okay. These are the ratios similar to what Jennifer showed. So the numerator in each of these is the different methods, and the denominator is method 2, because that's what the developers favored for the NGA. So it's using the average fault properties weighted by length and the total magnitude. So this is showing how these different methods compare then with that method 2. And again, this is the Hosgri and the San Luis Bay scenario. So let's get some negative values over here. This method.
Let's leave that one for
Okay.
a second there. So that top plot is saying method 1 versus 2 is not, 1 isn't conservative at all periods. It's going to change.
That's correct.
And this is, these are our choices right now, or the ways that we can implement it into the GMPEs and move forward. This is a potential impact on that particular scenario based on this decision. So we're back to our question, can these simulations inform us into a choice of these things rather than having the person running the hazard simply make that decision and charge forward. So that's really what we're going to try to get to here. So don't worry so much about the details. All of the physics gets more and more complicated, but can you tell me something better than us just choosing this and saying, I'm going to use SRSS because I've done that in the past, or I'm going to use method 2 because that's most consistent with what the developers did in their regression. However, there's only a handful of points that would have been affected by this, so they're really not, the development of their model really never addressed this issue and said, here's a objective evaluation of what to do. So.
Oh, and I also want to mention, I'm not showing any ratios with the simulations. In part, I'm doing this to be consistent with what Jennifer showed because she used method 2 as her denominator. So we're sort of trying to show the same thing. But also, I think we need to rethink what we put in the denominator then when we start using the simulation results. So that'll be coming up in March, right? Yeah. Okay, so this shows the results for the Hosgri combined with a splay on the shoreline fault. So method 1 is getting that closest point. Method 2 is the weighted average with the total area, or the magnitude estimated from the total area. Again, we have these differences here. We have the weighted average with 1 over r squared, and then we have the combined method and the simulations. I'll quickly just show the simulations compared with the different methods. And then this would be method 2 is in the denominator. So
can you
when
go
you
back,
have, okay.
go back one? Let's not go too fast, because on the previous one, I don't think the simulations were that much high, as much above as they are here. Is that right?
Okay, so this is the simulations.
I guess they are.
Here they are.
Too.
They're popping above here, but the other methods, at least in here, they're enveloped by the GMPEs. And they're
Okay.
higher out here.
Yeah, but we know about the long periods are
Yeah,
going to be higher.
so that's always
right?
going to happen.
So now can you go the same one for
Yeah.
shoreline?
And these
So
are the
now
same.
it's higher though at all of the methods,
Yeah.
right?
It is.
XSIM is doing
That's
that.
correct. But we
It's
we
lower,
saw
that looks fine, but the XSIM one is quite a bit higher this time.
XSIM is always high when it's close to the rupture plane, and this is Diablo Canyon, so we're really close to the rupture plane. It's particularly high right over it. We're not over it, but I think it's still high when you're close to the rupture plane.
This gets to the point of when we're comparing the simulation results, what's the denominator? Because we really need to be doing, I think, comparing more, what does the simulation give for the individual pieces in some way or some other, in the way that the ground motion would have been developed.
Right. So one approach would have been, say, to normalize this by the main rupture itself for each of the methods, right? And to see
Yeah.
what the increase is.
And that's, I
Yeah.
think, what we talked about doing for
Right,
March.
right. That just didn't get completed yet, but I think that normalization is really important. So we're not looking at differences in simulation versus empirical,
Mhm.
but effects of this parameter.
And the other thing I just noticed from here is look, all methods 2, 3, and 4 all use the combined magnitude. And it seems to be that that's, at least at low frequency, that seems to be a big factor, that the magnitude is the large magnitude in the comparisons. I don't know how the differences are between methods 3 and 4, but
Well, this,
at least at low frequency, it looks like the magnitude is a big player.
and I also want to mention, when your splay rupture is not complex, so when your splay is the same geometry as your main fault, these methods become the same. So that's why it's like that for this case. Okay, and I'll show the Hosgri and the Los Osos. And here we see a large difference here between methods. And that's because here we're combining, we have the Hosgri with a rate of 180 and a dip of 90, the Los Osos, dip of 60 and a rake of 90, and then we SRSS them to produce this. But here, when we use the weighted average, we have a magnitude 7.6. It's larger magnitude. It's a dip of, I believe, 79 degrees and a rake of 146 now. Okay, and then again, we see large differences over R squared and the combined methods. And then here are the simulations, and then simulations compared with the other methods. So they're much larger here for this method 4. They're way above at the high frequencies. And then here are the ratios. And so to just summarize, what I did is I took the maximum increase from these ratios here, just these top points, using method 1, the comparison between method 1 and method 2, to look at how this would change the hazard how this would change the ground motions at 10 to the minus 4. So this represents a change in hazard based on which method you choose to combine your GMPEs. And so, using my very uninformed probability of the splay fault rupture, this is assuming that 10% of the time a splay fault occurs. And so this would be the change in hazard that you would get between the two methods.
Change in ground motion.
Change in, I should have put hazard up here because I really want to say hazard. This is the change in ground motion, assuming that 10% of the time you get a splay rupture between the Hosgri and San Luis Bay. This is showing Hosgri with the Los Osos, and then the Hosgri and shoreline. And then for comparison, this is assuming that splays occur 100% of the time, what the change would be in ground motion. Okay, one thing I did want to mention, so now I'm going to show the differences in the ground motion between the different cases that we ran. But before I do that, I want to clarify something that I said earlier, because Brad Agard asked the question how the moment or the magnitude was computed. So what I said was we used the total fault area. So if we were going to have a splay between the Hosgri and, say, the Los Osos, we would use the total area to compute a magnitude, and then partition it based on area. That's true for some of the simulations we have recently run, because after thinking about it, we decided that was the approach we wanted to take. But when we set these up for the splay cases, we wanted to be able to use these same faults for the combined rupture, or for the complex rupture scenarios, and for the splay rupture scenarios, and use them independently. So the magnitudes are for each individual segment, using the area and Leonard scaling for each individual segment in the Hosgri. So when we sum up the moments, we're getting lower moment than we would have if we had used the total area to compute the magnitudes for these. So I just wanted to mention that. For the thin case, so what we did for the thin case is we used our preferred geometries. So we have the Hosgri fault. It has a length of, I think it's like 107, excuse me. And we have a width of 15 kilometers. So we use Leonard scaling then, using that geometry. Then for the thick case, we ran the Hosgri. We extended the width down to 22 kilometers based on the recommendation by Rob Graves for how to implement his model. And when we did that, for this case, we shortened the length of the fault to maintain the Leonard scaling. For this case, we extended the width to 22 kilometers, but we didn't then shorten the fault. We let the fault have the same dimension, same length, but we held the magnitude fixed for what we would have obtained with these cases, Leonard scaling using this. So the magnitude is 7.2 in all the cases for the Hosgri. 7.3. Anyway, it's the same magnitude. And here are the results we get. So this line, I don't know if it appears blue or black to you, but they are on top of each other practically. Very small differences. So we're obtaining about the same ground motions for these two cases. But if we allow a larger fault dimension with a smaller magnitude, so a low stress drop event, we're seeing a decrease in the ground motions there at long periods. So I guess this is sort of a segue into the discussion, because one of the things that we would like feedback on is, what is the appropriate way to model these things?
Let's go